Hi, I'm Chuck McCown. We build microtrenching equipment. I get asked all the time how how much longevity or life can you get out of microtrench blade? That's a complicated question to answer. And to answer it, I got to go into what you use to make a microtrench blade. So the wheel of the blade starts out as a sheet. We use super hard steel. This is the size of the sheet of steel that we use. Okay, this comes from Sweden, Hardox 450. You really can't use a harder steel than this, or you're going to have your blade crack and shatter on you. This is as we have experimentally determined. This is the ultimate highest strength you can use to build a micro trench blade. The other blades that we've had, we have micro trenching subcontractors and contractors bring us blades that are made by other people all the time saying, can you fix this? Can you rebuild it? Can you do something for this? Sometimes they have cracks. Sometimes they're missing segments. And so we generally test the hardness of the steel on those guys. And let me show you how you test the hardness of steel. All right, so this is the industry standard for testing hardness of steel. It's a Rockwell. It's an old Rockwell hardness tester, and what it does is it drives a diamond tip, a point, into the steel, and to see how far it penetrates. Now, this is a chunk of what we would call carbon steel or mild steel, or what is it, A something, A32, A36. Anyway, this is the most common thing. This is what the micro trench machines are made out of. This is what farm implements are made out of. You go down to the steel shop and you get a chunk of steel. This is what they're going to sell you. What you have to do here on a Rockwell test is you set a certain amount of preload. What I'm looking at is this little needle coming up approximately to that dot. And that just puts a certain amount of pre-stress. And then when it gets up close to it, then I turn this to where it says set. Now this is the set for the Rockwell C scale, which is up on the top, the outer edge. Rockwell B scale is designed for measuring different hardnesses of other things other than steel. So I've set this to set, and then I'll flip it here, and a certain weight forces that diamond tip to penetrate down into the steel, and then I'll remove that weight, and we'll see how far it actually penetrated compared to where it was set. And the outer scale here says 30, which is what I would normally expect to see on mild steel, 25 to 30. So that's mild steel. Now, we use Hardox 450, and you saw that big sheet outside. This is the same material. This is what we make the teeth out of, and we'll show you how it measures. When people bring these blades in from other manufacturers, we always rig up some kind of a stand here so that we can throw their blade on this machine and their teeth on this machine and see what they're using. And then I'll take the weight off of it and check this out. 43, Rockwell 43 scale. So that shows you the difference in the steels, and it shows you about how we measure the hardness of the steel. Those big sheets of steel, we cut them up into things that look like this. This is what we call the wheel, or the wheel blank, and this is getting ready for teeth. It's also being prepped for addition of hard-facing strips that will keep the sides of it from wearing down. If this wheel blank never gets thin, you can put teeth on it forever. You can rebuild these things forever. We have people with over 100,000 feet on a blade because they periodically bring them in, and we refresh the hard facing, and we put teeth on that are needed. But it all starts out with super hard steel. You can't use mild steel wheel blanks and expect to get the footages that we get out of our product. Okay, these are blanks that have been hard faced and ready staged for welding the teeth on. You can see these strips of this is This metal right here is added. It's a lot harder than the Hardox even. And this is a wear strip. It prevents the teeth. The tooth itself prevents the wear of the finger here, and then these pieces of hard facing prevent the wear down into the wheel. And beyond this point, there isn't much wear on a microtrench blade. It all happens like in the last 4 to 6 inches. But what we're trying to do is preserve this thickness so that you can cut off the teeth and weld new ones on forever. And as long as the blade never gets thin, you can rebuild it. That can't be said for mild steel blades. I don't care what you do to them, they will thin to the point where you can't fix them. It's just the nature of the steel. Nobody else that I've seen does both super hard steel and even super hard or hard facing on top of the steel. Everybody else just has a mild steel blank. Some of them stick a few pieces of carbide on the side. It's not very effective. So anyhow, we do what we can to make the best blade, the hardest blade, the longest lived blade in the industry. Each one of these blanks here is for a different machine, different size machine. We do Ditch Witch, all the Ditch Witch sizes, all the Vermeer sizes, some of the Tesmic sizes, Caterpillar blades. We do Brevard blades. We do Mac Brent blades. We do Hydro Wheel blades. So when you call and say, hey, you got anything on the shelf? No, we got this on the shelf normally. And when you say, well, I want a Ditch Witch blade, I'd come over here to this section. Well, which Ditch Witch blade do you want? Well, I want an MT26 blade, so I'll come over here to this section. Well, how wide do you want it? I want a 2-inch wide blade. Then we can prepare the blade for you. We take the tooth blank, and we put them in the milling machine, and it gets pockets cut into it for the diamonds. So there's other videos of this going on out there, but that's the next step. That's how we make the teeth that get welded on by the robot. Is everything on here? Everything is on here. Okay, one of her mica went. She's got one ready to go. I don't know if I'm good enough to do one of these. Should we give it a try? All right, let's start it up. All right, so this is where we actually make the teeth after the Hardox plate's been cut and it's been milled. We assemble them with a stack up of the Hardox tooth blank, carbide, flux, silver, mostly silver, bearing solder or brazing strips, more flux, carbide plate, carbide blanks, and these little black areas on the top are the actual diamonds. Now, I'm not the guy that normally does this, so I may ruin this tooth. Well, let's see. Let's see. It's been a while since I did one of these. This is it. Pardon? Drop it down in the... Okay, here we go. We're taking those tooth blanks. We're putting some flux on them. We're putting layers of silver bearing brazing compound. Then she's putting on this is a piece of tungsten carbide with a layer of diamond on the top. That black layer is a polycrystalline diamond. And we just call these diamonds or diamond inserts or inserts. So that's what does most of your cutting. The carbide pieces are there just to help the tooth survive the process, even though the tooth is already the hardest steel we can use for that without it becoming brittle. All right, she's going to put it in a coil. Those loops of the coil have water going through them, and they also have a high frequency AC signal going through them. It's called an induction furnace, and it heats up pretty quick, and it doesn't use any flame. And I think it's either 30 or 60 kilohertz is the frequency that goes through there. And what she's watching for is for everything to get hot enough for the brazing material to melt. And so we don't want to go too hot because the actual diamond can separate off of the carbide due to the fact that they have different coefficients of thermal expansion. But this is a process that it just takes some practice to learn how to use. And it's interesting, the coils don't really get that hot if they've got the water going through them. But what she's looking for is all of this stuff is movable and floating. And the floating is evidence that the brazing material is actually melted properly, and the flux compound has cooked itself out. You don't want any flux in the joint. You want nothing but the silver in there, and that's what it takes to put the diamonds on the tooth. Thank you. I've tried to add instrumentation, but it's just really a skilled operator knowing what the heck they're doing gets us the result we want. This is our cooling table. This is the pre and post wash process here. And once it's to this point, it's ready to go get welded on by the robot. All right, guys, you make noise now. Thank you. Don't have one going today, but I've got other videos on the YouTube channel showing this. This is the robotic welder, and we put those wheel blanks on here, and we feed them with the teeth. And once that's done, they get tattooed with a serial number, and they get palletized if they're being shipped, and they're on their way out. These are 1.5-inch blades. This is an MT26. This is an MT16. All that said, how long will a microtrench blade cut? How far will it cut? Well, that's still a really hard question to answer. Let's talk about a street. Hopefully your street's a pavement, right? It's got the surface that the cars run on. Well, or the trucks or the horse-drawn buggies, right? So what could that be made out of? Well, we were recently in Venice, and it's all cobblestones. Hopefully, you're not trying to microtrench in cobblestones. It could be concrete. A lot of concrete, total concrete streets out there. Hopefully, you're not trying to microtrench in concrete streets. What our blades are designed for, I wish I could do the real nice architectural detail here. There's patterns showing different types of materials, but asphalt, okay? 4 inches, maybe the 4 to 6 inches of asphalt, that's what we expect. That's what our blades are really, really super good at. But then, what do you got underneath the asphalt? If you're cutting with, say, 10 inches of cover or more, you're cutting down 12, 13, 14, 16 inches deep. So you got at least like 10 to 12 inches of mystery material here. Some cities we're hearing are requiring 18 inches of cover, so a 20-inch deep trench of even deeper. And we build the saws to go all the way up to 26 inches deep. Our two main saw depths are not just the saw blades, but we make the saw attachments as well, and we put them on tractors that we also supply. But we can go 16 or 26 inches. So mystery material. This makes the difference, how far you can trench without wearing out your blade. Most modern, newer roads are built with what's called road base, and road base has standards. I can't cite the standard numbers off the top of my head, but I've got a good friend right up the street here who has a nice big rock quarry, and he blends the materials to create the standard road base that places like Utah Department of Transportation uses underneath their streets, highways, and roads and interstates. I know it has sand. It has a certain amount of earth or clay in it as a kind of a binder. It has small gravel. I don't know what else. It has a certain amount of moisture content. It will compact to a certain degree. It will also drain to a certain degree. But there's been, centuries of people, clear back to the Romans, figuring out how to build roads and make them last, make them drain, make them sturdy, make them not sink. So anyhow, new modern road base, that's as far as my expertise can lecture on that. If you have new modern road base with decent, good what they call bituminous concrete, which is really nothing more than saying aggregate mixed with tar, which is what most of us call asphalt in the United States. It's capped with an asphalt surface. My blades last without any attention given to them. If you want to just run them and wear them out, they'll generally make 20 to 30,000 feet. However, if your saw operator feels for that wear strip on the side every day, and then you bring them to us before that's gone, so it prevents the blade thinning, we can replace the odd tooth that is worn off or broken. And if you do that, and it's generally intervals between 7,000 and 15,000 feet, okay? Bring them in. It costs you another $500 to $1,500 typically. New hard facing, replace the teeth that are missing, and you can just repeat, rinse and repeat, rinse and repeat. We've got several customers over 100,000 feet on the blade. Flip side of that, we've got customers in Puerto Rico where it's difficult for them to get the blades back, and they don't have a shop down there to rebuild these things. They just run them till they die. They have gotten 40,000 feet out of a blade. I think 20,000 is more of a reasonable expectation. Okay, but that's with good road base. People run into volcanic rock. They run into cobble. Cobble is a big enemy. They run into chunks of concrete, and the worst is they run into a old layer of pavement that's made out of concrete. Now, if you run into that, I would suggest going to some other different technology, like a rock saw. All the time, people ask me, like, well, why can't you just adapt concrete cutting saws and make a blade like the concrete cutting saws use? Well, okay, those saws, those diamond tipped, really thin concrete cutting blades, they run at like 3,000 RPM. A microtrench blade runs at 100, 150 RPM. Okay, I don't know if you saw the recent video of one of those concrete cutting saws that came off the machine, but it crossed a couple of lanes of traffic, a parking lot, and ran through a store. I mean, those things go fast. Yeah, you go buy a concrete cutting saw, cut a couple of strips, and jackhammer out the concrete. I would just suggest that you get a rock saw. The narrowest rock saw, which is normally about 3 inches wide, 3 to 4 inches wide, with the replaceable tips, and have a bucket full of tips, and just grind out that concrete. It's slower. It's a lot slower than microtrenching, but my microtrench blades won't last long if you get into solid concrete. You're talking 500 to 1,500 feet in a layer of concrete. They're just not designed for it. There's other manufacturers of microtrench saws that claim to be able to cut it. I would suggest please go to them for all your concrete cutting problems. You run into cobble. My blades cut cobble. Nobody's blades cuts cobble well. There are other companies, I think, that cut cobble better than mine. If you're cutting in cobble, you might get 3 to 4,000 to 5,000 feet before it's torn up pretty bad. It needs to be rebuilt. The concrete and the cobble, what they do is they knock those little diamond inserts that we soldered on with the induction furnace. They knock those clear off. They not only knock them off, but they take a chunk of the tooth with them. You can always tell what was happening when you have a damaged tooth, is that if the metal behind the pocket where that thing was brazed on, if it's all missing too, that hit something super hard and literally sheared that hard ox tooth material. It's impact damage. Impact damage, you're going to have it when you get into the cobble and concrete and the volcanics, especially up in southern Idaho that they're seeing up there. And you'll find that some streets in some cities will only have like 1,500 feet of just tougher than the hubs of hell type cutting, and then all of a sudden they cut 5,000 feet and it's just going great. So you never know what you're going to run into. Your saw operator can feel it. You know, they crank their speed up until the blade starts snagging, and when it's harder, you can't go as fast. So again, I don't have an answer. I can tell you that in normal cutting conditions, with normal blade maintenance, our blades have lasted more than 100,000 feet on multiple occasions. I can tell you that our blades last longer than everybody else's blade that we've measured. We get a lot of anecdotal evidence back from our customers. Of course, they've got some brand loyalty, and they're telling me happy news. Rarely get any unhappy news from our customers. So I believe our blades are harder than any of the options out there. I believe our blades will last longer if properly taken care of. I believe our blades will last longer even if not properly taken care of. We know they're the speed records, 6,110 feet cut in a day with one of our blades on our speed conversion saw attachment. Okay, so they cut faster. And we're consistently told they cut cleaner edges, margins, and leave the ditch cleaner. However, a big function of that is the vac. You got a good guzzler, good high CFM vac. That'll keep your ditch clean. It'll allow you to cut faster too, because a lot of the blade speed, cutting speed, is determined by how fast you get the dirt out of the ditch. If you don't have a very good vac, you're not pulling that dirt out, and that causes that whole snagging issue that limits how fast you can go. So you got a big old guzzler on this thing. You no longer have that problem. Now you're limited by your tooth angle geometry, the torque on the blade, and a few other factors. You know, the overall design of the blade, that limits you. I'd like to see what the limit is. You know, 30 feet per minute is one of the higher speeds we've seen anybody cut with our blades on our saw. I'm curious to see, and that was cutting 16 inches deep. I'm just really curious to see how far this technology can be pushed. So I don't know. Did I answer your question? I get this query. I usually write some of this stuff down in an email, send it to somebody, and I decided I don't want to have to repeat this. I'm just going to make a video. Maybe it answered some questions. Thanks.